Okay, our focus in this chapter is a chi-square test. It's kind of tricky. It's not really called a chi-square test. It's going to focus more on the chi-square distribution, at least these two, the 11.2 and 11.3 sections. Goodness of fit test and the test for independence or test for homogeneity. And then the last section in this chapter is called analysis of variance, also known as ANOVA. The goodness of fit test and the test for independence uses the chi-square distribution, and the analysis of variance uses a whole new distribution that we don't have to worry about, and we're going to rely on the calculator to do all the work for us. But it all boils down to p-values, and a small p-value will have you reject a null hypothesis, and a large p-value will have you to fail to reject, and then we will going to base our conclusions. So it's all, again, falling on that 8-step process, or if you've learned to trim it down to 3 steps, that's fine. So we're going to look for all these, or these three, for these 3 topics, we're going to look for a null and alternative hypothesis. We're going to look for finding a test statistic and a p-value, and then we're going to look for finding a conclusion based on your statistics. So let's find out about the multinomial experiments and the goodness of fit first. The proportion problems that we did kind of relied on the binomial distribution, where you have something that went one way or the other, and then you just took the proportion that that satisfied whatever it is you're talking about. Like, for example, how many people voted? How many of the voters voted? So the binomial distribution says that it falls under one of 2 categories. So they either voted or they didn't vote. So it's a success or a failure. So it's one of those 2 categories with a fixed number of trials and all that other stuff, constant probabilities. We're going to extend that idea to beyond just one of 2 options. So our first discussion will be on what's called a multinomial experiment, which is just like the binomial experiment, except instead of falling into 2 categories, we're going to fall into more than 2 categories. And then we're going to discuss, we're going to make things a little bit more complicated beyond that and talk about contingency tables. Now, we have talked about contingency tables before. I don't know if you remember, but we did probability. One of your quizzes, as a matter of fact, and I think one of your test questions, was about a contingency table. You have a table, rows and columns, and then you added them up, and then you found probabilities. So now we're going to do the same thing with these contingency tables. We're going to take a look at a 2-way frequency table, and then ask questions about that, how things should happen, or what we would expect to happen in a table like that. And in both of these examples, they use what's called a chi-square distribution, which we should be familiar with already. I showed you the table A4, and for me, since I don't have some of the stuff in my calculator here, I didn't really bother to load up my calculator with those programs that you guys have. But I'm going to rely on the chi-square distribution and looking at the table. But if you guys have the program already installed in your calculators, I think it's called goodness of fit or something like that in your programs. You'll take advantage of that, and it'll make lives a lot easier for you when you're in the test. What? Best fit. Best fit. Okay, and then the contingency table, since it is a few rows and a few columns, it'll rely on what we call matrices in math, and your calculator also has that. All right, let's skip over this. Let's talk about the multinomial experiment. And let me just put a star on the third condition over here, which is the only thing that's different between this and the binomial experiment. The multinomial experiment has a fixed number of trials, and you know that we're going to call that n. The trials are independent. And then here, all outcomes of each trial must be classified into exactly one of several categories. So instead of having one of two categories, we're now looking at one of several categories, which makes it multi versus a binomial. And then the probabilities for each category remain constant. So that's kind of analogous to the binomial distribution, where you have a constant probability for success. And then the 1 minus p, or the q, was the constant probability for failure. So here you're talking about a bunch of categories now, each of those categories having a constant probability. So based on this type of an experiment, a multinomial experiment, you're going to ask yourselves, is it following that particular pattern where it satisfies those constant probabilities for each of those categories? Does that make sense? Kind of made sense to me, but. And we'll see that when we're doing the hypothesis test for this, that we're actually going to examine two types of problems. One where there's the same probability for all the outcomes, and then the other one will be a set of distinct probabilities for each of the outcomes. And then we'll see when we dive into an example. We're going to take a look at the example in a slide, but I'm going to go through the example in the slides really quickly, because then I want to jump to the homework and do an example from the homework. I think that's a little bit more fun. So here's an example. And you don't have to write this down. I won't, again, I'll just breeze through the slides. This is on, I'm not going to write anything down here. And this is something that you can download. When asked, people often provide their weights. They're somewhat lower than their actual weights. So how can researchers verify that weights obtained through actual measurements instead of asking the subjects? And when you say your weight, you don't say, oh, I'm 187 pounds. You say either 180, 185, or 190. Probably 185, right, if you're 187. So what they do is they usually round down to the nearest 0 or nearest 5. And so when you actually collect these subjects and put them on the weight scale, the last digit of their weights can be any number between 0 and 9, right? But when they report their weights, a lot of them are either going to say, 180 or 185 instead of saying 187, which is what their correct weight would be. And so the claim that they have here is that test the claim that the digits do not occur with the same frequency. Now, by looking at this table, just by kind of eyeballing it, it's clear that the 0s and the 5s have a lot more frequency than the others. So you can probably guess that the conclusion for this particular problem is that, yes, based on this data, it looks like we can support the claim that they don't occur with the same frequency. So that's just a quick glance at this information. We'll go through the slides will go through the actual hypothesis test, and then we'll do one. The first thing that they want to verify is like the requirements to make sure that they satisfy the multinomial requirements. And so this is a multinomial requirements. And just a little note here, if this was in fact distributed evenly between all the digits from 0 to 9, then each of those digits would have a possibility of 1 in 10 for a person reporting their weights. It's just spread out evenly. So constant probability over the spread out. So the test we're going to use is called the goodness of fit test. So this is an actual definition. Write notes again. This would be a good thing to write down. The goodness of fit test is used to test the hypothesis that observed frequency fits some claim distribution. So the claim distribution in the example that we would have would be and then would be describing the last digit of their weights. And then the distribution we're saying is that this is supposed to be a uniform distribution. So 1 in 10, 1 in 10, 1 in 10, 1 in 10, etc., up to 9. So this is an example of a distribution where you have a uniform distribution, and then the goodness of fit test will test to make sure that this is actually accurate and this is true. So we're going to need, because this is a whole new test, is like the correlation problems that we did. We got introduced to a whole new set of data. Here, we're kind of getting introduced to another set of data. The data kind of looks like just a frequency table, which is what it is, really. It's a one-way frequency table. But the categories are now nominal categories instead of quantitative. They're qualitative categories. So the calculations would be a little bit different. So we're going to get introduced to this new notation. Capital O will represent a list of numbers that would describe the observed frequency. So this, in the past, or in chapter 2, or wherever we start talking about frequency tables, I guess that should be a CIS. Frequencies. O would be the frequencies that you observed in your frequency table. And then E would be based on the distribution that you're claiming, what should be the frequencies that you would expect. And that's E. It's a list. So O is a list, E is a list. K is a number of different categories that you're looking at. And then N is a total number of trials, and the total number of trials that you've collected. So we got the fixed number of trials, just like in binomial distributions, that was N. And so we don't have P here because we'll consider it different P values, different probabilities for each of the categories. And so we can't just say P and Q because we have more than 2 categories. So we can say P1, P2, P3 for the probabilities. Is it next? Nope, sorry. P1, P2, P3. And then depending on how many categories we're dealing with, it has to be more than 2, right? Otherwise it's just a binomial distribution and it just becomes a proportion problem. And I'll use K for the kth category. So I have K probabilities that would match up with each of those categories. These are I'll put constant in parentheses, but these are the probabilities for each category. And I don't know why they didn't put that here in the notation, because I think this is how we're going to, or one way to represent the hypothesis, the null hypothesis.
So in the requirements you said you were going to use a constant probability for each trial?
Yes.
So what are these?
These are the probabilities for each trial that will remain constant throughout your experiment. Well, in the first example, they are all the same. I see the same. There's two sames there. They are all the same in a sense that for each time you run a trial, they'll have an equal amount of chance, or they'll have a P1 or P2 or P3 kind of chance to land in one of the categories. The other interpretation of the same says that these are all equal to each other. And that's not what the fourth bullet point is saying. Okay. When they say the same, that means the P1 is going to be P1 for category 1 for the whole time that you're going to run this experiment. Now, these may be the same depending on the scenario, but they may all be different. So it depends on what the scenario is. All right? That's a good question. And I'll try to come back to that question when we start doing examples. So here are one of the two possibilities for a goodness of fit test. One possibility is that all the frequencies are going to be the same. This is one of the same ones. So that means P1, P2, P3, oops. And all those probabilities are all the same. So this is one type of goodness of fit test. Depending on how many probabilities you have, they could all be the same. In the example that they're doing here, they're assuming this scenario, that they're all the same. So if they're all the same, then your expected frequencies will be the total number of experiments that you have divided by the number of categories. I guess total number of trials, sorry. Divided by the number of categories. So if you had 200 people in this trial, or 200 things, whatever it is you're dealing with, and then you have 5 categories, then you take that 200 and separate it all into categories. And so that would be what you would expect if you have a uniform distribution, if you have an equally likely chance for all of those things. Now, there's another scenario for a goodness of fit test. And if you have a goodness of fit test that says that each of the categories are going to be different, then your expected frequency would be the total number of trials times the probability for each category. So n again is the number of trials. And then p would be the probability for each category. Let me erase this sub I over here because that might just get confusing. That's a scenario of that. Let's say if you sat near the front of the class, then you have a 50% chance of passing the class. If you sat in the middle of the class, let's say you have a 30% chance of passing the class. And if you sat in the back of the class, then you have like a 20% chance of passing. That's probably not true. Maybe it is. I don't know. But in any case, each of those categories now, the front, the middle, and the back, would have a different probability of passing the class. And so this scenario over here would be one of those scenarios where the expected frequencies are not all the same. Okay, so those are our two possible scenarios for our goodness of fit test. All right, let's take a look at the details. We have O, we have E, and then we have N. So the requirements, there's a set of requirements just like before. The data should be randomly selected. I was going to say simple and random. I guess that can be considered simple also. The sample data consists of frequency counts for each of the different categories. So there's a frequency count for each category that exists. This is just kind of saying that it is in fact a multinomial experiment. And then the last one, it's like the other one where it's bigger than 5 for each category. Then you have n times p is equal to 5 business, or n times p is bigger than 5. And then here they mention expected frequency for a category is a frequency that would occur in the data. There's no requirement that the observed frequencies must be at least 5. So that's an interesting idea that we don't need to worry about. So what this is saying is that we just want a sample that's large enough. We just want a data set that's large enough. So that's one of the dangers in statistics. If your sample's too small, it's really not going to be representative. So this is large enough data. Okay, I think the next slide should be the hypothesis test, or the test statistic. The test statistic looks like this. Each of these represents a list of values. When you have a frequency table, you have categories and then you have observed values. So these are your frequencies. And then you're going to find your expected values. Expected frequencies, sorry. And then so you'll have a list of O, observed values, and then you have a list of E, expected values, or observed frequencies and expected frequencies. And then you're going to put them into this summation formula to help us calculate all that stuff. And what you're going to get from there is a chi-square value. And you know that when you're dealing with chi-square value, you have to refer to the table A4. And A4 has degrees of freedom. So note that our degrees of freedom is not n minus 1 anymore. It has been n minus 1 for a while, and then last time for our t distribution we went to n minus 2, which we didn't really care too much about. But now it's not even using the sample size, it's using the number of categories. So our degrees of freedom will be dependent on the number of categories. And then the second condition with a critical value is that usually when we look at critical values, depending on the tail, we either look at the left side or the right side. So the good news here is that your goodness of fit test will always be a right tail test. So we're always going to look to the right, which is going to make our, if you're going to rely on the table A4, it's going to make it easier for us because the table is always going to be looking at the area to the right. But hopefully you won't have to rely on the table because you'll just find the p-value somehow. All right, let's see. Let's skip over this stuff. I think these things will be good to look at once we do an example. But this is where, reject and fail to reject. This is stuff that we have already talked about. But they're just putting it in this context, so I don't think it's worth discussing. But here's that example. So the example, your hypothesis test is either going to, your null and alternative hypothesis will either look like this, where they're all equal to, or they'll be kind of stated in a way where you're going to say that P1 is equal to something, P2 is equal to something, P3 is equal to something else, etc. Your alternative hypothesis will almost always look like this. At least one of the probabilities is different, or at least one of the probabilities is not equal. So this is how our null alternative hypothesis would look like for the goodness of fit test. And let's try to stick with the same symbols, like P for probabilities. And notice the H1 is not in mathematical terms anymore. It's in words, right? But these words are the exact opposite of what the null hypothesis is saying. Saying this is not the same as saying what you see in words. Saying not equal to for all of them is not the same as saying this. It's not the exact opposite of H naught. So that's why we don't want this. Okay, so it's better to state it in words because that's going to capture the exact opposite of what we're trying to say in the null hypothesis. All right, so a couple of references for us. With an alpha, if it's not stated, alpha is going to be 0.05, and then your degrees of freedom will be k minus 1. Since there's 10 categories, our degrees of freedom will be 9. And then you'll find this from table A4. That the chi-square critical value is going to be 16.919. So the other thing that we need is we need to figure out the count. So what they did was they added this up, and they got 80 apparently. So there's 80 of them, and we're assuming, or the null hypothesis is assuming that all the frequencies are the same. So we'll use that formula E is equal to N divided by k. So there's 80 trials in our experiment, and there are 10 categories, and so that's how they got the 8. So our observed frequencies should be 8 for all of them. All right, so if you were to do this by hand, if you remember the test statistic, it's something like I'm sorry, this isn't observed. Let me erase this. This is expected. This is observed. The frequency that's given to you in the problem is the observed frequency. The frequency that you would have calculated would be the expected frequency. So if you remember the test statistic, it's like O minus E quantity squared divided by E or something like that. So if you were to carry this out, you would add more tables. If you were to carry this out by hand, you would add more tables. But we'll have a calculator take care of this for us. All right, so the test statistic, this is a table that I was talking about. We got observed, we got expected, we figure out O minus E, and then we square that, and then we divide by E, and then add them all up, and you get the critical value, or not the critical value, but this is your test statistic. So based on your test statistic, you compare it with the critical value that we saw. That critical value is fairly small. Critical value was 16.919. Let's see. So I would have drawn the graph, but they didn't do it. So the critical value is 16.919, and so this is a critical region, and it's always a right tail for this. And then you look at your test statistic. Test statistic 156.5 is way out in the critical region, so we're going to reject the null hypothesis. And because this doesn't really rely with equality and stuff like that, usually you can just conclude if you reject the null hypothesis that you can probably say that the alternative hypothesis is true. Okay, they have another example here. The second example that they have deals with where the frequency is not all the same, but I think I just want to leave this presentation for now and go to our homework problem set and do one of those. It did. So it fell in the critical region. So because it fell in the critical region, where you rejected the null hypothesis. Yeah, it's way out there. So large values, usually large test statistics, means there's a big difference between what you're expecting versus what you actually found. Am I plugged in? battery's going to die. What are we going to do? So let's do the same type of problem where, oh, thanks. Let's do a problem similar to what we just did, and then we'll do another problem that's going to be a little bit different. Okay, so the author collected data on birth, month of actresses who won Oscars at the .05 significance level. Test the claim that the Oscar-winning actresses are born in different months with the same frequency. So, some keywords to look out for. Same frequency. Do the data give reason to believe the Oscar-winning actresses would be more likely born in some months more often than others? So because we're dealing with the same frequency here, we're assuming that we're in the same frequency, we can set up a new list. This is the observed frequency that's given, and then our expected frequency would be in this list that I'm going to come up with. So my expected frequency would all be the same. So whatever number I'm going to have here will be the same number for everything. And I need to know how many of these things I have. And then I have 12 categories because there's 12 months in the year. So let's punch this in our calculators. So I'm going to put this O in list 1. My observed frequencies, 16. And then a quick way to add this is just to try to figure out what the sum is. So I'm going to go back to the home screen, second function, and quit. And then I'm going to ask it to add up by L1. I think I need to go to second function and stat, which is a list. Go to math, and then sum. And then I want to say L1. So I have 198. Were you guys adding them up, and it looks like it would be the same? So it looks like there's 198 of these people. So the other thing to do is to divide it by 12. I got 16.5. Now, for this, it's okay to have decimals, and so your your expected frequencies for this would be 16.5, which means you're going to make a list here. 16.5, 16.5. Well, I'm not going to write everything down, but you get the idea that it's all going to be 16.5. So what you can do is, since you are going to be dealing with lists, it might be good to go back and for L2, put in 16.5 12 times. Now there's an easy way to do this, but I don't remember, so I'm just going to type it all in. And make sure you don't go past 12. That's it. So your lists are the same size. So if you remember the test statistic, the test statistic is going to be the sum. This is a big sum of O minus E squared divided by E. And the way I'm going to do that in my calculator is I'm going to literally just change this summation sign with SUM, sum, and maybe 2 parentheses. So O is in my list 1. E is in my list 2. And then I'm going to square that and divide by E again, which is in my list 2. So sum, remember how to find sum? Second function in stat or list, go to math, and then the 5th one down is sum. Open up another parentheses, L1 minus L2, close the parentheses. You can do a caret 2, or there's an x squared button in your calculators that you can just press, and then divide by L2. So I got 26.36 or 363. Would probably be more appropriate. Now the hard part about this is we got to dig out your table A4. I'm going to pick that up in the appendices, or maybe I can just get it from here. Copy of the table. No. Ah. I don't know what to do now. Maybe I could just use the board. I got all excited. I got this break in case of emergency. Brand new. Nah. According to Benford's law, by the way, says that in all the numbers that you see all around, like street addresses and things written down on paper and stuff like that, it turns out that the leading numbers don't all have the same distribution. The leading numbers don't all have the same distribution. And what comes out the most is the number 1. So according to Benford's law, a variety of different data sets include numbers with leading, the first digit, the leading digit that follow a distribution shown in this table. So 1, the number 1, turns out to be something that happens most common. And then there's 2, 3, 4, 5, all the way up to 9. So 9 is the least common that would happen. So this is a perfect example where we have things that are not all equal. Probabilities not all the same. So now this is different from the problem we just did, or the 2 problems that we just did, because all probabilities are different. An investigator analyzed leading digits of the amounts from 792 checks issued by 7 suspect companies. The frequencies found were 3, 15, etc. And those digits correspond to the leading digits of 1 through 9. If the observed frequencies are substantially different from the frequencies expected with Benford's law, the check amounts appear to result from fraud. Use a 0.01 significance level to test for goodness of fit with Benford's law. And does it appear that the checks are the result of fraud? So, unlike the first problem where I kind of just jumped on this thing, I'm going to try to do this systematically. I'm going to start with a null and alternative hypothesis. So the null hypothesis is not going to be P1 equals P2 equals P3 equals P4 because they're all different. So I'll state this a couple of different ways. One way is kind of a long-winded way, but I'll say P1 equals 30.1%, comma, P2 equals 17.6%, comma, and do you know where I'm getting all those numbers from? Those are the expected probabilities. And right now they're percentages, but we can easily change them into probabilities and stuff. Another way to state this is to say that the probabilities are stated as above. If there's 8 of them, 9, 10, that's a lot to write down. I think if there's 3, 4, or 5, you can easily write that down. You just write down what I started to write down here. Or you can just say it in words. The probabilities are what they're supposed to be according to some law. And then H1 is always going to be the same. At least one is different. Probabilities is different. So that's my statement. Now the next step is to calculate the test statistic and stuff like that, or even just to get it ready to put it in your calculators so you can use the best fit program. But I'm going to, don't want to recreate this whole table, but I think we might have to. So rewrite the table. I was going to write it going down, but I'll write it going across. Leading digit. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And the first thing we want to put is our observed probability, or observed frequencies. And that is given to you not in a table, but it's given to you as part of your paragraph. So you have to be careful in finding out where those things are. So the frequencies were found to be, so that's the observed frequencies. That's what they found. So 3, 15, 3, 87, 243, 390, 8, 20, and 23. So I was expecting one to be large, and it's not. So this is probably going to be one of those we got to reject the null hypothesis business. This, by the way, the observed frequencies would be the frequencies that you would probably send to L1. Now, the expected frequencies are going to be, if you remember the formula, E is equal to NP for each of those probabilities. So what you need to do is you need to take your N is equal to, they gave it to you, that was nice, you don't have to add it all up. N is equal to 792. So you take 792 times 0.301, that's the 30.1%, and that's going to go into the first slot over here. 792 times 0.176, that's 17.6%. That's going to go in the second slot right here. And then you go on and finish that off. The 0.301 comes from the probability of 0.176. So you can do that one by one. I'll show you a little shortcut using the calculators. It's not much of a shortcut, but anything would help, right? So I haven't put my list down yet, so let me start with the L1 by putting that list down. And that list is 3, 15, 3, 7, 3, 390, 8, 20, 23. So nine values that I got. Now, I'm going to do it like this, a little bit differently. I'm going to go to L3 first. And in L3, I'm going to put these probabilities down. So I suppose you could do it the way you're doing if you're doing it that way, but this is just another alternative. And I'm going to put the probabilities down as decimals instead of percents. So 0.301 is 30.1%. 0.176 is 17.6%. 0.125, 12.5. Now be careful with the single digit percentages. Now this is 0.097. 0.079, 0.067, 0.058, 0.051, and 0.046. So what I have in L3 are the probabilities. And what I'm going to do is I'm going to jump to L2, because the way the pred-int problem works, or the pred-int program, it relies on you having the list in L1 and L2. Okay, so I'm going to put this in L3, and I'm going to go back to L2. I'm going to move my cursor up to L2. I can clear it. I suppose I can clear it. Maybe I should clear it. But I want to make sure that my cursor is up where it says L2 and not down here in the list part, but actually up in L2. And I'm going to say basically N times P. So my N was 792. And then I want to multiply that with P, and that's a probability from each of those categories that I put in L3. So I'm going to put L3. By putting L3 down, I'm going to say 792 times the first one, 792 times the second one, that's going to go in the second slot. 792 times the third one is going to go in the third slot, etc. So if I just say the total N times P, and my P is a list of probabilities in L3, I can just say 792 times L3. And when I press enter, if you did this by hand, this is probably what you'll get, or something very close to this. So I'm going to write down a couple of them. I would be expecting 238.39 for the first one, and 139.39. 238.39, 139.39, and 99. And I'll just put etc. to get the rest of that information. Okay? So I don't know if that was easier for people, or if you just want to type it in by hand, that would be fine too. The list L3 came from the probabilities that they gave us. There's no official label for it. No, I would just call it P. That would be my P list. So let's see if I can recreate that. $792 times L3. So this is the observed, this is the expected, and then these would be the probabilities. Okay, so from here you can just go to program best fit, or you can do it the older way where I would add up a whole bunch of things to get the critical, to get the test statistic, and then compare it to a critical value. Oh, I have best fit. So why don't I just use best fit? So with the best fit command, I'll say best fit. The number of categories that I have, there's 9 categories. And the p-value, is it 0 exactly? 0 plus. So it turns out that the p-value is so small, the calculator is just going to round it off to 0. But remember that it's not 0 unless it's absolutely impossible. So best fit. 9 categories. Your test statistic, your p-value, PV is 0 plus or 0.0, something that would tell me that you know that it's not 0 exactly, it's not impossible. So based on this number, this is clearly less than any significance level that we would choose. Based on this, we would say what? We would reject the null hypothesis and then end up supporting the claim, which says that they're not all the same, which makes this a fraud. All right, let's see if we can finish answering the questions in the homework. We reject the null hypothesis. There is sufficient evidence to warrant the rejection of a claim that the leading digits from a population comes from Benford's law. It does appear that the checks result from a fraud because they're not conforming to Benford's law. So let's include that in our notes. So it looks like we didn't really identify what our claim was. So the claim was the goodness of fit for Benford's law. So the claim should have been the null hypothesis in this case. So since we rejected the null hypothesis, our conclusion is that there's sufficient evidence to warrant the rejection of the claim. Okay? So the best fit program, really handy. It allows us to find out not only the test statistic that we would normally do by hand, but it also gives us the p-value. And you can find the p-value using the chi-square distribution, but we don't need to mess with that, so I'd rather not deal with that. Okay, any questions about goodness of fit? So that's a goodness of fit test. Let's go into the next section. Should probably